want to start with a little warm up, which is a little exercise about quotient spaces, but we'll use in a second when we talk about homotopy. So the warm up is as follows. So let's take x to be the unit square. And we're going to consider the following partition on x. So here's x, and the partition, so we're going to group all of this part of the boundary into one subset, call that A, and every other point is going to be its own partition element, singleton. So partition P, it has the set A, and it has little x for x not in A. So in this case, when there's only a single element of the partition which consists of more than one point, we write x mod A for P with the quotient topology. Okay, so intuitively, x mod A is what you get from x by collapsing all of A to a single point. Okay, and so now you might take a second and think about what space you think you get when you take this unit square and collapse this 3/4 of the boundary to just a single point. So the claim that I'd like to explain is that x mod A is topologically equivalent to the closed disk. Okay, so the picture is, well, you collapse A to a point, and, well, okay, you still have the picture. Now this black segment of the boundary becomes a circle, and on the inside you have the interior of the disk. Okay, so we want to prove this topological equivalence, and right, so that we have this standard way of doing this. So proof sketch. So the first thing, which will make things a little bit easier, right? So the thing we want is, well, we want a map x to the disk whose surjection whose partition is P. Right, so then by the quotient identification theorem, that tells us that P is homeomorphic to the disk. Right. So for this, it's a little bit helpful to right, so equivalently, since the unit square is topologically equivalent to the unit disk, so this isn't hard to show. It suffices to find a surjection from the disk instead of x to the disk. With the property that, well, okay, let me draw it this way. So Now let's fix some arc. So A is going to be an arc here, and it's going to map to a point. So let me call this map something, I guess, Q. So Q of A should be a point, and Q restricted to the complement of A is injective. Okay, so if we have these two conditions, then the associated partition is going to be the one that gives, well, yeah, there's just one non-trivial partition element, which is A, and then the rest of them are singletons. And so that's, then we conclude that the space we get by collapsing this arc A to a point is just the disk. Okay. Right, so all that remains is to define this map Q. So let's do this on another page. Right, so defining Q. D squared. So let me do this in a picture, which will hopefully be convincing. So, well, we know what we need to do on the arc A. So A has to go to a single point. And, well, we just want a way to map the rest of the disk in a bijective way to the complement of this red point here. Yeah, I guess I should have said here that Q restricted to A complement, this should be a map from A complement to D squared minus this point, which maybe I should call it a name. Let's call it P here. And that this is injective. And since the map is surjective, it should be a bijection. Okay, so that's really what we want. Yeah, I mean, before what I had written, it would have been possible that you might have points of Q in A complement that also map to this point P, but we don't want that. Because otherwise we don't get the right partition. Okay, so right, so let's see what we want to do here. So this boundary portion of the boundary, well, we know where it must get mapped to. It must get mapped to this segment here. And well, so, okay, let me just draw this picture. So like an arc like this should get mapped to an arc sort of like this. And right, we can kind of imagine what the map should do by drawing how arcs, so arcs inside of the circle, like how I'm drawing here, should map to circles which are tangent to this point P. And by should, I mean, we'll define it to be that way. And well, if we construct a map like this, then, well, it has the property that we want for every point not on A here. It maps into the complement of P in a, well, yeah. This map has the properties we want. Maybe let me not spell it out, since it's really just understanding this picture. And I guess the only thing that you might ask is why this map is continuous. I mean, that's an important thing that we need. And I think away from any point other than P, it's sort of easy to see that this map is continuous. You know, I mean, if one was to write down explicitly how this map worked, it would be even easier. But since we're just working with pictures, let me just try to, yeah. So maybe let me explain like near P. So if you pick some open set around P, well, the preimage of this is going to be something like this. The intersection of this open set with the disk, excuse me, and that's open. Okay, so okay, maybe this is not, well, if you're not convinced, you should think a little more about this. But this is a sketch of an argument. Okay, right, so that's the warm up. Now let's move towards the fundamental group. So let me recall a few things. So the fundamental group of X based at P, which is denoted pi1 of X comma P, P is just some point, is the set of loops. So these are continuous maps from the interval into X with the property that they start and end at P. So they're loops based at P. And we consider this set up to equivalence relation given by homotopy. Homotopy through loops that are also based at P. And last time we showed that this set has a group structure. So this is the fundamental group. And with respect to this group structure, the homotopy class of the constant map is the identity element. The constant loop, yes. Right, and so terminology, I think I mentioned this last time. If F is homotopic to the constant, we say F is null homotopic. Okay. So a couple of observations. Which are the main things that I'm going to explain today. So the first is that, well, instead of thinking of the fundamental group as maps from the interval, we can think of the fundamental group as maps from the circle. So there's a bijection between maps like this, as I wrote before, and maps from the circle into X with the property that G sends a base point, let's say 1, to P. So here I'm thinking of the circle as the unit circle in the complex numbers. So that 1 is a point there. Right, so the claim is that these are in one-to-one correspondence, and moreover that homotopy here on the left-hand side, it corresponds to homotopy through maps of the circle, which is, you know, okay. Yeah, maybe, yeah, let me first explain this bijection. So the way this works, given f on the left-hand side, how do we get a map G? Well, so we have, sorry, let me just say it this way. Define G S1 to X, which actually I'm going to call it F hat. By F hat of e to the 2 pi I t is f of t for t in 0 to 1. So this is well defined. So f hat is well defined because, well, the only issue is that when t is 0 and t is 1, this is the same point. Right, so I mean, it's well defined because f of 0 is equal to f of 1. And it's continuous because we have the following diagram. So we have, let me draw it this way, into X, this map F, and have S1 and F hat here. And this Q is the quotient map. Q of t is e to the 2 pi I t. And right, so we know that f hat is continuous if and only if this map F is continuous. Right, so f hat is continuous. Yeah, let me write this here. Let me rearrange. By a lemma that we proved last week about quotient maps and continuity. Okay, so this is the first observation, that we can think of elements of the fundamental group as maps of the circle. Oh, right, I only did one direction. Let me also say conversely, if you have G, a map from S1 into X, we can define well, G hat is Q composed with, G composed with Q. So this is the same. If we start instead with a map like this, then we can get a map on the interval just by taking the composition. And if G has this base point property, then F will have the correct base point property. Okay. All right, so that's the first observation. The second observation is that, well, with respect to this bijection, we can reinterpret what it means to be null homotopic. So if you have a loop X, which is null homotopic, homotopic to a constant. This is true if and only if the associated map f hat from the circle extends to the disk. So that there's a, let me write it this way. So we have f hat. There's the inclusion of the circle into the disk as the boundary, and to extend means that there's a map phi, so that, well, phi has the property that phi restricted to the boundary circle is f hat. Okay, so this is saying that if you have a loop, so say we have x here, and we have some loop here. If this loop extends to a map of the disk, then that means f is homotopic to a constant. And I mean, the reason why you should believe this, so, right, I guess this is like the backwards direction. If f hat extends to a disk, then f should be homotopic to a constant, because then you can just sort of shrink f along small loops here. Okay, so this is at least one direction, at least the idea. But let me point out that, I mean, f isn't assumed to be, well, okay, yeah, I don't know, f in general is not some injective map, so maybe it's hard to tell just from drawing a picture that the map extends to a disk. Okay, so let's actually write down a careful proof of this. Okay, so proof. Let's first do the forward direction. So let's fix f null homotopic. So then that means there's a homotopy. So there exists homotopy. Which we can picture like this. So a homotopy is a map of the unit square into X, and it's a homotopy between F and the constant map at P. So I'm just going to label each of these three sides gets mapped to P. And so then we get the following. So we have the following. So we have this map, this homotopy is a map, let's call it capital F into X. And it's constant on these three sides. So let me call this A. And so let me call this square Y. So we have the quotient of Y by A, which we proved in the warm-up is equivalent to the disk. And since capital F is constant on A, we can define a map on this quotient map, or quotient space, which I'm going to call phi. So the way phi is defined, phi of an equivalence class little x is f of x, and phi of the equivalence class A is just f of A, which is just identically P. Okay, and now what we want to show is that, so, right, so our goal here was to show that F hat extends to the disk. So we just cooked up a map from the disk into X. Observe that we want to say that phi restricted to the boundary circle of the disk. So this is, well, the boundary of the disk corresponds to this green segment here. So this is, right, under the quotient map, this green segment maps to a circle. And the map on this boundary, if you think about how things are defined, is exactly F hat. F hat is that induced map on the circle. So F hat extends, which is what we wanted to show. At least this is the one direction. All right, so now let's do the other direction. Maybe let me just erase this. So now let's suppose that, so assume F hat extends. As in this diagram here. And we want to show that F is null homotopic. So we need to construct a homotopy from F to the constant map. And the way we're going to do this is as follows. So let me first draw a picture. So what we have is a map of the disk into X, that's phi. And on the boundary, we know this map is doing F hat. So, well, what we can do is map the square into the disk in the following way. So this is going to map to the boundary circle. So the red goes to the red. And then well, I need each of these green lines to be a loop based at X, or based at the base point of X, which is P. And I can do that if at the endpoints, if I map them like this, since this base point on the disk maps to P. Okay, so this suggests defining F of S comma T, this is the homotopy, to be phi of, so 1 minus T e to the 2 pi I S plus T. So this first piece, this is mapping to the circle of radius 1 minus T, but then we shift by T so that this circle meets, all the circles are tangent to this point here. Right, so let's just check that this does what we want. So F of, at time 0, this is phi of, so this term vanishes here, and we're left with e to the 2 pi I s. So this is on the boundary of the disk, and so this is f hat of e to the 2 pi I s. And remember how f hat is defined. F hat is defined like this. And so its value is f of s. Okay, so at time 0, we're just doing f. At time 1, we have just phi of 1. So this is the point 1 here. And that's equal to p. And now to be a homotopy, we also need that f of 0t and f of 1t are both equal to p for all t. So, well, let's just see what this expression gives. So f of 0t, when we plug in s is 0, this term becomes 1, and we just get phi of 1 is p. And similarly, f of 1t is also, so now this is still 1, is phi of 1 is p. Okay. Okay, so this homotopy does exactly what we want. It's a homotopy between f and the constant map at time 1. And this is the picture for how to think about it. Okay, so this proves the this 2 second observation. So now I want to give a couple of examples of using this fact. So example. So let's take RP2. And I want to think about it as a quotient of the 2 sphere. So remember, this is lines through the origin in R3. And it's also a quotient space of S2 by the antipodal map. And the way we reasoned about that was, so every line through the origin in R3 intersects the upper hemisphere, or intersects S2 in 2 points, antipodal points. And so that's why these are the same thing. Or we could also think of this as the 2-dimensional disk. This is the upper hemisphere. Modulo antipodal points on the boundary. So that's like this upper hemisphere. Every line goes through the upper hemisphere at least once, and then it goes through points in the XY plane, points on the hemisphere in the XY plane twice. Okay, so this is RP2, just a reminder. So now let me tell you a couple of loops. So first, consider paths in S2 given by, so G1 of S is going to be cosine pi S sine pi S 0. So this starts, so the way G1 looks, it starts here and then goes halfway around the circle. This is G1. And let's define G2 that goes all the way around. So cosine 2 pi s, sine 2 pi s. These are defined on the unit interval. Right, so let's write Q for the quotient map from S2 to RP2. Sending a point to its equivalence class. And right, so if we, now let's define F1 as Q compose G1 and F2 as Q compose G2. So these are both loops based at P, where P is the image of this point, the space point here, 1, 0, 0. I guess, yeah, so this is X, Y, and Z axis here. Right, these are, so okay, the main, yeah, so these are loops because, well, here, G1 is a path that goes from 1, 0, 0 to minus 1, 0, 0. But these are the same point in RP2. So when you project, this becomes a closed loop. And, well, note that F2 extends to disk. Maybe I mean F2 hat, the associated map of the circle, extends to the disk because G2 hat does. So G2 is this loop. So, oops. G2 is the loop, or G2 hat. Well, the image of G2 is this loop that goes all the way around the equator. And, well, clearly this bounds a disk. It bounds exactly the upper hemisphere. And so this map extends to a map of the disk. And so then, right, so if phi is a map of the disk into the S2, yeah, right. I guess we could write this precisely. Yeah, so let's actually write this precisely. So define phi from the disk to S2, sending r cosine 2 pi s, r sine 2 pi s to the same point in the xy plane. And then we want this to land on the sphere, so in the last coordinate, we should do 1 minus r squared. This is this map, so note that phi restricted to the boundary of D2 is exactly G2, right? And the boundary is when r is equal to 1. And then we see exactly the formula for G2. Or I guess it's G2 hat. It's a map of the circle. And so then if we consider Q composed with phi, this extends so this is a map from D2 to RP2, and if we restrict to the boundary, this is Q composed with G2 hat, which is F2 hat. Okay, so this is explaining the claim that F2 hat extends to the disk because G2 hat does. Right, and the other thing I want to observe, well, okay, so let me just draw a picture to explain what I've explained so far. So I wanted to explain this as rigorously as possible, but now let's move towards a picture and understand how we can sort of see this intuitively. So here's RP2. It's what you get from the disk by identifying the boundary with these side identifications, as we've seen. And the image of F1 is this loop here. And the image of F2 is the full boundary. I mean, that's sort of how these things were defined. So here's the image of F2. But of course, I mean, these, this edge is this edge. But okay, so first, in this picture, we see that F2 extends to the disk because here's the disk that it extends to. F1 does not clearly extend to the disk because, well, I mean, this doesn't bound a disk in an obvious way. But I guess the other thing I want to observe is that F2 is F1 concatenate with itself. Because, I mean, these two edges are the same. So F2, it does this loop, and then it does this loop, but this loop is the same as this loop. So it's the same as F2 is doing F1 and then doing F1 again. I mean, this vertex, these two vertices are the same point. This is both P. I guess I can label them both as P. Okay, so we've just shown rigorously that the equivalence class of F2 is the equivalence class of the constant. So okay, so altogether, thus, in the fundamental group of RP2, base point, this point P, we have the equivalence class, the homotopy class of F2 is equal to the homotopy class of a constant because F2 extends to the disk. But on the other hand, it's the homotopy class of F1 concatenate with F1. But this is the product in the fundamental group, so this is F1 squared. So this shows rigorously that this loop F1 has order 2 in the fundamental group. So, okay. All right, let me do one more example. And now I'm going to try to do things a little more pictorially. So, right. So this is a common thing in topology. You do arguments. Well, right. There's sort of two routes to doing arguments, both of which are rigorous at the end of the day. One is arguing carefully through formulas and so as we did here at first, and then the other is arguing through pictures, which if you understand the translation from the picture to the formula, seeing the picture, you could write down the formula. but often it's easier to work with the pictures. So in the second example, let's consider the torus, which is product of circles, and consider two loops, F and G, where F is doing the first circle direction and is constant in the second circle direction. I guess it should be 1 if we're on the circle. And G is constant in the first circle direction and traverses the second circle direction. So the picture is, so we have one circle direction like this. Here's F, and G is something like this. Okay, and here's our base point here, P, which is equal to the point 1, 1. So the thing I want to observe is that F concatenate G, concatenate F in the reverse direction, concatenate G in the reverse direction. This is homotopic to the constant, which we can see pictorially because this loop, so if we cut F and G, cut this torus along F and G, what we get is exactly a square here. So F, F, G, G. And this loop that I've written down, well, what is it? So it's first you do F, then you do G, then you do F backwards, and then you do G backwards. And to see that this loop is null homotopic by our second observation, it's enough to observe that this bounds a disk, which this disk is staring at us in the face right here. Right, so this is sort of the use of the lemma. Now, we don't have to write down a full homotopy. You just say, look, there's this disk that this map extends to. If we had to write it down, the formula for this disk, we could, and I would encourage you to do so. But I mean, look, it's right there. I mean, I'm pointing at my screen. It's right there. Okay. So consequently, so thus, in the fundamental group of the torus, we have F times G times the homotopy class of the reverse of F. Remember, this is F traversed backwards, is the inverse of F. So the reverse, its homotopy class is the inverse. And so then we get this formula, which implies that F times G is G times F. I'm just moving this bit to the other side, which is to say that F and G commute, or these homotopy classes. Okay, great. So I want to contrast this with the Klein bottle. So on the other hand, for the Klein bottle, K, so remember, K is obtained by a different side identification, like this. So on the Klein bottle, it's not clear if FG, well, let me say it this way. Well, yeah, it's not clear if FG is GF since the loop F, G, F bar, G bar doesn't obviously extend to a disk. I mean, maybe it does still extend to a disk, but it doesn't obviously extend. I mean, you should think about this. I mean, you go F, G, and then you go along F, F inverse, but then you need to go along G inverse in reverse. But that's not, yeah. So, I mean, the thing that you see that extends to a disk in this picture is, right, so instead, we see that if we do F, so here's F, then we do G, then we do F in reverse, and then we do G going forward. This extends to a disk. I guess technically I should say that the corresponding hat version of this, but okay. So in the fundamental group of the Klein bottle, we have this relation, that F, G, F inverse, G is the identity, which implies that FG is G inverse F. Okay, so that's not quite saying that F and G commute. This is some other relation. And so a remark, so we know this relation holds, and well, we're not so sure if this relation holds. So if this other relation does hold, if F and G commute, or let me just say it this way. I mean, if, yeah, F and G commute, let me write it this way. Then, well, so then we have these two equations. Both have F times G on the left-hand side. So we can just say, then we have G times F is G inverse times F, G inverse on the outside. But this is a group, so you can multiply by inverses. So this implies that, yeah, so we can cancel these F's. G is G inverse. But that's the same thing as saying G squared is 1, is the identity element of the fundamental group. So if both of these relations are true, then this G element has order 2. Later we'll show that that F and G both have infinite order. Hence, it's not true that F and G commute. So F and G don't commute. Okay, so do you follow the logic? If F and G commute, then G has order 2. Later we'll show, in fact, G has infinite order, so F and G actually don't commute. So the Klein bottle its fundamental group is not an abelian group. There are elements that don't commute. Yeah, so that's the last line in my notes. Hence, pi1 of the Klein bottle is not abelian. Okay.